Timer off. Okay. Welcome and hello. This is a lecture in HEC ResSim. We're going to be talking about release allocation and hydropower. These are two topics that I just haven't included in a lecture before, so I decided to tackle both of these topics at the same time and create a little example problem to demonstrate both of them. It's lecture number 8. That doesn't mean you have to have done any of the other lectures. These are drop-in lectures, so we will all get started from the same starting files and work through all the individual steps together if you want. All right. Let's see here. If you haven't already checked out the YouTube page, the channel that you're probably watching this on, you can click on playlists and get a number of other lessons and videos in HEC ResSim, such as HEC ResSim lessons is right here on the right, kind of behind my face. Sorry about that. And here are some exercises and some support videos, in addition to playlists that cover a number of the other HEC software modeling programs. In the bottom of the screen is the web address where we're going to get the starting files, boschsolutions.com. Also, if you want to send me an email with any questions or anything, my email is in the bottom center of the screen right there. Here is the web page, and if you click on services for Bosch Solutions and then scroll down, here are the drop-in lectures. This is the lecture we're doing right now, and in the future I plan to have a whole schedule of lectures in the days and weeks in advance, but I just don't have that at the moment. So go ahead and click on this Excel file for data, and then also the zip file to download the starting ResSim files. If you're visiting this at a time and you don't see any lectures here, you can just click on the link that says download lecture files. These should be the exact same files that we download for whichever particular lecture that you want to engage in. The purpose of some of these starting files is just to kind of get us started, so we're not wasting 5 or 10 minutes drawing out a system that we've covered in previous lectures and, of course, are covered in some of the other lessons. All right, so let's go ahead and get started. I am going to bring those two files I downloaded to the screen here. Let's open up the Excel file first and see what we got. Along the bottom of the Excel file, we have the different worksheets, and they are labeled L1 through L8 at this moment because I have just completed and prepared lecture 8. So here's the L8 right here. Go ahead and click on that, and I'm going to hide my ribbon here. This is the data that we're going to be using in this particular lesson. So just keep this Excel file handy. We're going to reference it and copy data from it into ResSim a little bit later. Right, so let me just move that there. All right, so that is the Excel file. And then here is the lecture file. This is the starting worksheet files, watershed files. I'm going to go ahead and move these to a location on my computer where I want to store them permanently. I don't want to just keep them in a zip file on my desktop. So I'm going to just drag those into what will be my project directory. And then boom, those are copied over. So I can now just move that out of the way and delete the zip file. All right. I do have a chat open also if you're watching this on the live stream. So if you have any questions, feel free to uh, write me a message and I'll read it. One of the purposes of doing these lectures is to get a little bit more real-time interaction with my viewers. Otherwise, the lessons and the exercises on this channel cover a lot of the topics and the editing is a little bit more precise. In the live lecture, you're going to have to watch me fumble around a little bit. I don't have the luxury of editing out all my faux pas. All right, so with that ado, with everything out of the way, let's go ahead and get started on our lecture number 8, where we talk about hydropower and release allocation. Go up to File, Open Watershed, and then navigate to your project, and then click on the project.wksp file, and then open. All right, so here is the file. Here's the watershed setup module. Here's the reservoir network module. I'm going to load in my network one. Boom. Now we have some edits to make to this network one. Looks like CP1 has already been assigned our inflow. So local inflow CP1, that's good. Now the reservoir has some edits that we need to make. So I'm going to right click, edit reservoir properties. We have a dam and the geometry is already there. So that is actually the first table in the Excel file. We don't have to use that. And then here is the dam. This is the geometry of the reservoir. Here's the dam face. And now we need to add some controlled outlets and our power plant. All right. So to do that, let's go right click and click on the dam, right click, and then we should be able to add a power plant. Another way to add the power plant is just to come up to dam and then add power plant. It's the exact same thing. And boom, here is our power plant. It's nested under the dam in our physical reservoir tree node diagram off to the left panel. And then we have a number of tabs up here for outlet capacity, efficiency, and station use, and so on. We're going to fill these out one at a time, starting with the outlet. So let's bring that Excel file up right here. And then let's see, here is the reservoir max capacity. So we have the elevation versus the max capacity. And I don't need to highlight the head in column 8, just the values here in column 6 and 7. So I'm going to scroll down and Control C to copy. And then move here, Control V. Boom, here is our data. The number of gates, I'm going to set this to 3. And then I'm just going to leave all the other settings as default. So I'll click Apply, and that is our power plant. There are a number of other tabs, like I mentioned, but before we tackle those, I want to add the controlled outlets for a couple other different locations in the dam face. So take notice that the invert of this power plant is 13. Yeah, so we'll get to that a little bit later, but just remember 1380. I'm going to create a couple more controlled outlets, or I guess, yeah, so what you're seeing here is basically the controlled outlet interface with all the power tabs associated with it. But I'm going to create 2 controlled outlets at a little bit higher up elevation in the dam face. So to do that, I'm going to go dam, right click, controlled outlet. For this controlled outlet, I'm going to paste in the data from the next table over. So again, here is the Excel file. Let me just scroll over. All right, so here is the controlled outlet. This is going to have an invert of 1400. So I'm just going to copy that, paste it in right here. I'm going to say it has 3 gates. So that looks good. And just to be explicit with the labeling, I'm going to rename the controlled outlet to something like CO at 1400 as my invert. And sort of be consistent, I'm going to rename the power plant as well. I'm just going to call it PP at 1380. That's the invert. And then one more controlled outlet at a little bit higher elevation will be at 1420. So right click, add controlled outlet, and then let's just rename it now since that's what I'm thinking about, CO at 1420. And then back to the Excel data, that's this table right here. And it's going to have 3 gates as well. So let's paste that data in, change the number of gates from 1 to 3, and boom, we're good. So apply. This interface right here we're seeing for the controlled outlets is the same thing that we see for the power plant in its first tab, outlet tab. But now let's go ahead and define some of the other properties of our power plant. So this next tab over, the second tab is our capacity tab. And what we want to do here is provide ResSim the capacity data. So I'm going to say it has a max capacity of 5 megawatts. And the variable capacity will be defined based on reservoir elevation. As you can see, there are a number of other options to choose from. I'm going to go with elevation. And now we have a table of data to provide for elevation versus capacity. So this is, I think, also in Excel. One second. Yes, it is. Okay, so we want to paste in columns 18 and 22 that correspond to the elevation and the power in megawatts. So I'm going to do this one column at a time here because I just didn't format the Excel file to put those 2 columns next to each other so that I can't really copy non-adjacent cells. All right, so there's the elevation. Let's go back to Excel. Can you see that all right? Oops, sorry, out of view. And then here in column 22, I'm going to highlight and Control C and then Control V. All right, so there is that elevation versus power generation capacity curve. And yeah, it should be linear once it's non-zero, of course. No, it's not linear. It's not linear. All right, that's good for the capacity tab. Apply efficiency. All right. So what I'm going to do here is say that efficiency is also a function of the elevation. And here I need to provide data for the efficiency table. So as the flow rate increases, the efficiency increases, generally speaking, and that is the next table over. Here's the power plant efficiency in columns 24 and 25 of the Excel. Control C to copy, and then paste. Very cool. If you're lost on the Excel, by the way, I am using worksheet L8 here. So after you open the file, click on L8 for lecture 8 file data, and then you'll be up to speed with us here. Okay, let me just toggle over. All right, the last table here in the Excel is actually the inflow data. I already have this data saved in a DSS path, so we don't have to use this, but I just included it in case you wanted to come back and change it or add another column with other data or whatever. And then here is the plot. Okay, so I think we're done with the Excel file in this exercise. We can move that away. There's one more tab for power plant that I want to define data for, and that's station use. And I'm just going to say it's a constant 5 CFS for the station use power and apply. All right. Another way, actually, you know what? I have my notes to define it as a function of release. I misspoke. And so what I'm going to do here is just say 0 and 0. And for some reason, it doesn't give me another row. I'm not sure if I'm doing something wrong because I want to define additional rows. Maybe if I paste in data. Okay. So this is just on my clipboard from the other table, but I wasn't sure how to get another row. So I just wanted to manually enter data. And maybe if I closed it and opened it up. But anyway, 0 to 0. And then if there's a 1000 CFS release, we'll just say it's 20. So that's just a 2% loss. Okay. All right. I'll click apply. And next, let's move over to the operations tab. The first thing to do here is say operations new. And here I'm going to define an operations set OS1. Now I'm going to be real boring with the zones in the top of zone elevation. I'm just going to use the default zone names, flood control, conservation, and inactive, and define a constant top of zone elevation for the entire year. So I've used some of these numbers before for previous lectures. So just bear with me. 1480 is going to be the top of the conservation zone. So that's going to serve as the guide curve elevation. And 1380 is the top of the inactive zone, which, wait a second, flood control. Okay, so it looks like that didn't save. And apply. Okay, cool. So here are the 3 zones all year long. Nothing fancy there. All righty. Let's see. Cool. Now, what I'm going to do later is check out this rel alloc tab for release allocation. And I'm not going to do anything with it right yet because the default release allocation is balanced, which means equal flow through all of the different structures in the physical tab. So we have the dam face here, and then we have the power plant, and then the 2 controlled outlets. So we're going to just go with the default, which is balanced, and then run the results, come back and change it to a different release allocation. I'll show you how that works. All right, so that's the topic of the lecture. We're talking about power plants and release allocation. And if you have any questions, go ahead and type them in the chat because I got that open over here in my other monitor. All right, next up, what we want to do is create an alternative. So I'm going to click OK on Reservoir Editor, then Network. I'm going to save all those edits. Click on Alternative, Edit. All right, and then to create a new alternative, I'll go up to Alternative, New. I'll just call it Alt1, and it will be based on my network 1 right here, and then click OK. Zoom to the top. Sometimes these forms don't resize, so I have to kind of keep in mind you guys can't see everything I can see sometimes. The Run Control tab is the first tab we want to define. I'm going to say the time step for the computations will be 1 hour, and then I will leave everything else just as it is for the default on this tab. The next tab over is operations. I'm going to set the operation set to OS1. That's our one and only operation set. The look back data, this is where we define the starting conditions that's going to be in place during the look back time period just prior to the actual start of the simulation. So for the pool elevation, I'm going to set this to 1480 because that's our guide curve elevation, the top of the conservation zone. And then what we also have to say is what is the release through all 3 of our outlets? I'm going to save the alternative and come back to this because what I want to do next is look at that inflow data with a little bit more precision. So let me go to our project directory. And if you do, you should see a DSS file called data.dss. So if I open that up, I've got this one path. And like I mentioned, this is the flow rate that's going to be flowing into CP1. We're going to assign that to our alternative in just a moment. But what I wanted to look at was starting conditions so I could think of what the look back data should be for the starting release. So the actual number is 100. It starts at 100 and then it starts going up. So 100 CFS is going to be the sum of the release from all three of my outlets. And I could assign it to all to just one particular release, like all to the power plant or all to the 1400 or 1420 um, controlled outlet. But what I'm going to do is just sort of distribute it evenly based on the elevation and then the flow rate. So I'll say something like, I have in my notes 48, 28, and 24. So something like that is about even based on the flow capacity and the starting head of 1480. All right, so let me save that. The last thing I need to do here for defining an alternative is to assign that CP1 inflow to our time series dataset. So to do that, I'm going to click on this particular row for CP1 inflow. And then down here, there's a button for select DSS path. Go ahead and click that. And then I'm going to open up and navigate to that same DSS file. There it is. Here's the path we were just looking at. When you click set path name right here, that will make that assignment. So boom, that's in place and we're good to go. So save the alternative, close, save the network. I don't think I need to do that. I think it was already saved. And now we're ready to create a simulation. If there's any questions about the reservoir network, let me know. I've got an eye on the chat, or you can, of course, write any comments down in the main comment section if you're watching this video after the live recording. I should have it available. And okay, so if there aren't, let's go ahead and move on to the simulation module. All right, this is where I want to create a simulation. So we'll go simulation new. I'll just call it sim1. And then for the starting uh, date and time, we need to define the date and time data right here. I'll say January of 2020. That's the first time step that corresponds to the flow data. So it's important to make sure the flow data and the simulation date times match up. Otherwise, you're going to get a runtime error. All right, so we'll say 1 o'clock or the first beginning of the second hour. And then for the very first hour of what will be a 5-day simulation, I forgot to mention that, 5 days of simulation for 120 hours of data, we're going to just start at the very beginning, which will be midnight. And then the last day will be 05 January, and that'll be at 2400 hours. Okay, that looks good. We're going to use alternative 1 and click OK. So here is our network once again. Here is the simulation tree. So I can just right click and compute. And I forgot to do something. Okay. So I needed to add a tailwater to the power plant. Forgot about that. You don't need to add tailwater if it's just control outlets, but the error message reminded me of something I had in my notes, but I just skipped over. So we can just do that edit right here in the simulation module. I'm gonna do right click, edit, run, and then click on reservoirs. And then for the power plant, I'm just going to right click and add a tailwater elevation. I'm just going to be simple about this and add a constant elevation of 1380. There's other options for a downstream control, rating curve, and so on. But this isn't really a lecture on tailwater per se. And yeah, 1380 is what I wanted to do. Okay, so that should work now. I'll click apply and OK. In the bottom right, there was an apply and OK button, if that was out of view for you. Sorry. OK, and then compute. Okay, cool. So it looks like that was the problem and problem is resolved. Let's click close. And now let's look at some results. So right here, I'm going to right click and plot. This is a pretty boring plot, but probably still a good one to start with. And it's worth mentioning that this flow rate here is the sum of all of our outlet structures, the power plant and the two controlled outlets. So the inflow is what we're seeing in black, and then the release is exactly the same thing, what we're seeing in green, and it's going to maintain that constant guide curve elevation of 1480. All right, so pretty boring, But where things get a little more exciting is if we look at the releases. So I'm going to right click on the reservoir, come down here to plot releases. And now this is interesting. What we see is the individual release, not the combined release for all of our, let's see, can you see the legend there? There we go. For all three of our outlet structures. There's the power plant, which is in green. And then in red, we have the controlled outlet 1400 invert. And then in blue, we have the controlled outlet at 1420. Now, all three of these lines, all three of the outlet structures share the exact same flow rate, as you can see, except for the majority of January 4th here. And the reason for that is simply because there's just not enough capacity, meaning at that guide curve elevation of 1480, we have a max capacity of, let's see, this is 231 for our outlet structure, the three gates at an invert of 1420, and then the three gates at an invert of 1400 have a max of 267. That's where that maxes out. And then it looks like we never actually hit the maximum here. It doesn't look like there's like a top plateau here for the green line, which represents the power plant. So that tops out at about 447, it looks like. 447, yeah, about 447. If we wanted to actually get these numbers and confirm, we could just look into our physical tab of the reservoir once again. So if I go physical tab and then click on 1420 right here at an elevation of 1480, 231 is the max capacity. At 1400, the next controlled outlet, and 1480 corresponds to 267. And I am actually kind of curious, the power plant 1480, 450. So we were at like 447. It looks like we only had like another 2 or 3 CFS of available capacity. Otherwise, we would have started to deviate from that guide curve elevation. We would have actually increased our storage above the desired amount by a little bit. Okay, I'm getting a little bit off on a tangent. Let's check out some power numbers now. If I go right click on the reservoir here with our stored results using the same default balance allocation and click on plot power, here is, yeah, so it bumps up right at the ceiling there. That's pretty cool. Boom. This top plot here shows power versus time. Now there's a line here at the top, which I've just highlighted. This is the maximum power capacity. And then the actual line that shows how much power we're generating over the course of that 5-day simulation is shown right here. And because we're just about maxing out the flow, let's see, this line right here. No, I'm sorry. The flow through the power plant right here is almost at, what did I say, 450? It was 447 instead of 450. Basically, we have almost 100% plant factor, or 1 basically, because it's a decimal from 0 to 1.0. So that's cool. That's good. That's the power data. Another way to look at power data is to look at the reports. So if you go up here to reports and then click on power summary, this is a good one. This tells us a number of things. There's columns for average, max, and min over that 5-day simulation. And what I want to focus on is the power generated and the plant factor. So power generated is right here. The average power generated is 1.21. And then the plant factor is 0.36. So over the 5-day simulation, 1.21 is the average power in megawatts. 0.36 means we're utilizing about 36%. There's a few other values here like the flow rate, the average flow rate, the max, the min. Some of these numbers are the same for like the generating efficiency is always going to be the same amount because that's based on the water surface elevation, which is constant for the whole simulation. Same with the head, it's based on water surface elevation. Okay. All right. So what I want to do here in the remainder of this lecture is to talk about the different release allocations, modify those release allocations, and then see how that affects the power generation, because I think we can do better than 1.21 as our average. And how we're going to do that is simply push more water through the power plant as opposed to um, letting it flow through the controlled outlet structures. In fact, this next alternative, if you will, or this next simulation run is going to max out our power, at least using the methods we have available to us for release allocation. So let's go ahead and do that. It's going to be called sequential So I'm going to just make the edits right here in the simulation module. I'm going to edit run reservoirs. And now I'm going to come over here to the operations tab. And then I'm going to continue to work with no rules. Typically, if you have rules involved, those would overwrite the release allocations. So to demonstrate release allocation, I'm just going to click on release allocation, leave the rules alone. There are a number of rules we could use specific to power plants, in fact, but ignore that. So release allocation, and then I'm going to come up here to the allocation menu and click on new allocation set. All right, so let's go ahead and name this sequential. Okay. So the sequential um, release allocation is name sequential. If I click on reservoir, there's only one way for water to leave the reservoir. That's through the dam. So we have 100% balanced method. There's sequential, balance, and step. We're going to use sequential, but on the next step down, since this is sort of trivial. All the water leaves through the dam. What we may see is a diversion or maybe a dam to a different downstream river. But for us, we're just going with one dam to a downstream single reach, no diversions. All right, if I click on the next icon down here in the tree, we now see the three different outlet structures, the power plant, and then the two controlled outlet structures at their different invert elevations. And then right now we're using a balanced method of 1, 1, and 1, which just means equal flow through all three. But what I want to do instead, and I can change this. So for instance, if I wanted it to be 60% through the power plant, I could just say 3 right here. 3. Okay. And then 1 and 1. So it doesn't have to add up to 1 or any particular number. It'll be normalized. But we're not going to deal with that. Let me change that back to 1. Okay. And I can also change the other numbers. But what I really want to do is change this to sequential. And this is sort of the easiest way to just say, send all the water through whatever the top structure is. And then when that maxes out in capacity, send the remainder through the next structure down on this list. When that maxes out at capacity, use the next structure down and so on. These structures can be reordered. So for instance, if I wanted all the water to first go through the controlled outlet of 1420, I would just select it, use the arrows over here on the right to move it to the top or the bottom, and just reorder it that way. But I'm going to leave it as it is. This default listing order was what I want. So that looks good. Let's uh, let's go ahead and run the simulation and then see what we get for our releases through each of these control structures, and then of course the resulting power generation. So click apply. Oh, click apply. I'm sorry. Down here in the bottom right, there's a button for apply. I just sometimes zoom in too far, and then I'm going to click OK. All right. So now we're ready to click OK, and then compute. All right, that looks good. Close. Right click. Now I'm just going to go straight to the releases. And now we have a different looking plot here, right? So what we have is the colors are still the same. What you're seeing in the green line is now the flow through the power plant, which is what we wanted to maximize, which means if this power plant line is not up at the maximum of 450, then the release through the other two structures will simply not even exist. They'll be down at 0. And that's what we see here. So when this is not at 450, 0. When this is not at 450 for February 2nd and 3rd, the flow through the controlled outlets is also 0. What's happening? Nice to see you in the chat. If there's any questions, go ahead and type them in the chat. And then also, when we do max out at 450 CFS through the power plant, then the red line right here, this represents our flow through the control outlet at the 1400 invert. And then the blue line here is the flow through the controlled outlet at 1420. So as you notice that we have enough capacity in the power plant and the controlled outlet at 1400 for this peak in the inflow hydrograph at the end of Jan 1 and early Jan 2. However, this flow at during January 4th, we actually max out our controlled outlet at 267, and that means we need to start releasing water from this from the controlled outlet at 1420. Right, so that's how that works. That explains that. If you want the actual numbers, you can go up to File and then Tabulate. And then here are the release values for the power plant, controlled outlet 1400, controlled outlet at 1420. All right, let's take a look at the power plant. Here's the power plot. You can already tell that we're generating more power than we were when we used the balanced release. So again, here is the power generation, and then we can tell that the average is going to be greater than 1.21. The average is probably going to be closer to like 2.5, I'm guessing. And then here's the ceiling again, which is about 3.6 or something, 3.4, 3.32. Okay. All right, let's go ahead and look at the power report. So report, power summary. Okay. And let's see. So yeah, we have an average power generation now of 2.61. That is quite a bit more than what it was our first time at 2.21. It's more than double, basically. And then our plant factor is 0.78. So that's much better than what it was at 0.36 from the balanced release allocation. So yeah, go ahead and check out those numbers if you want. Now the last release allocation, and I'm sorry we hit the half-hour mark, but I'm just going to talk for another 5 minutes or so. The last release allocation I want to describe here is edit run reservoirs. Click on um, sorry, it's called stepped. I'm getting ahead of myself. So here's sequential. I'm going to go allocation, new allocation set. I'm just going to call it stepped. Okay, so stepped is now loaded as our current release allocation. And then if I click on the dam here, I'm going to change from balance to step. Now this table right here is sort of similar to ResSim's explicit system storage balance method. So we can kind of control at each step how the release is allocated between the different structures. So for instance, this top row here is sort of fixed at 100%, 100%, 100%. And if you wanted to say use the balance method, we would just have 0, 0, and 0. That's pretty boring, and that's sort of that defeats the whole purpose of having a table here. But basically, all the flow rate would increase based on the capacity of that particular outlet structure from 0 to 100% for all three structures simultaneously. But what we may want to do is, again, prioritize that reservoir, the power plant outflow, in which case we could say 100. And then I'll just say 100 all the way down so we can add some different, some detail to the curve. And then I'll say 0 and 0. And then between the structure at uh, the controlled outlet at 1400 and 1420, they'll both start at 0. They'll both end at 100. And then once the power plant has hit 100% capacity, then maybe what we could do is just share it 50-50. So I'm typing in 50-50 here on this row. And then the next row, maybe once they're both at 50% capacity, we could type in 100 and then leave 1420 at 50%. So we'll see what this looks like. Hopefully I'll demonstrate it. I'm going to say this is want A, B, C, and D. So once we look at the results, keep that in mind when we're looking at this table. Okay, so I got a request about releasing water from a reservoir in a flood situation. Absolutely, that's one of the whole purposes of building reservoirs and dams is for flood control. So stay tuned. I will see. I mean, a lot of the exercises in my HEC ResSim, um, oops, in my HEC ResSim playlist uh, do cover that particular topic of flood control. So I'll mention that at the very end. Let's go ahead and finish up the lecture though. So let's see here. I'm going to click apply and then OK. And then OK here. Let's see my screen. There we go. And then let's go ahead and compute using the stepped allocation for releases. And now right click. I'm going to click on plot releases. All right, so this looks a little bit different. The green line for our power plant, that should look the same, which is right up here. That's maximizing because we set it at 100%. However, once we're at maximum capacity through the power plant, we share 50% between the red line, which is the controlled outlet at 1400, and the blue line, which is the controlled outlet at 1420. Now, you may notice that they're not exactly the same. Let's focus in here at the end of January 1. We have, again, 1400 outlet, 1420 outlet. And it's not sharing 50-50 regard to flow, it's sharing 50-50 with regard to capacity. And the capacity at with through the controlled outlet at a lower invert has a slightly higher capacity. So that's why these lines are not on top of each other. All right, if we scroll over to and then zoom out a little bit, here is January 4th inflow. And the red line here, it looks like it tops out, it maxes. And then that's when, again, these are the two controlled outlets. Red is 1400, blue is 1420. Right here, like on January 3rd, before this inflow at all, would be considered that row A in the table. And then row B would be right here, where both of the the controlled outlets are increasing from 0 to 50%. And then row C would be right here where the 1400 continues increasing to 100%, and then the blue line at 1420 maintains 50%. And then row D finally, if I'm making any sense, um, is when we max out right here at 267 CFS flow through the controlled outlet at 1420. And that's when the remainder of the flow goes through this controlled outlet at 1420. This is 1400, I'm sorry. This is 1420, so that'd be range D. And then C, B, and then A again. So anyway, if that didn't make sense, I could probably explain it a little bit better, or by all means, go ahead and send me an email or a comment in the questions down below, and I can help make that make sense. But anyway, that is all I had prepared for this lesson. We went a little bit over, and feel free to ask some questions in the chat. I did get one question with a request about making a video about releasing water from a reservoir to prevent flooding. So that basically involves looking ahead and predicting storms and future inflows and releasing water, perhaps below the guide curve elevation, to accommodate that extra storage you may need. But yeah, otherwise, thanks for joining me in this lecture. Check out the Bosch Solutions webpage. Again, if you want to click on services, and then the files are right down here if you wanted to do this exercise for yourself. And otherwise, that is all I had prepared. Thanks for joining me on this lecture, and have a great rest of your day.